Hello and welcome to Orgo 1 Lesson 6. Continuing with molecular orbitals, you had to practice this. There's no walking in like sketchy from the last lesson and getting anywhere in this lesson. You had to practice this. So we should be very well versed in the simple shape of an s orbital or shape of a p orbital. It's easy stuff. Should be considering how to draw molecular orbital energy diagrams for like lithium, beryllium. And now we're getting into the 2p elements, which is a little bit more challenging perhaps, because boron, for example, has an electron configuration of 1s2, 2s2, 2p1. And because boron has the 2p electron configuration, it's making use of the p orbitals, which are a little different. Because you know, there's just one, and it can combine only in one kind of a way. One lobe to one lobe, sigma. But a p can combine in a one lobe to one lobe sigma or a two lobe to two lobe pi, and that changes a lot. So let's see how that works out. If you had a boron approach a boron and you have a B2, what kind of molecular orbital diagram will that have? So boron has a 1s orbital, like we've said. And then it has a 2s orbital, like we've said. But then it has three 2p orbitals. The other boron is the same, of course, as the first boron. So same energy level for the 1s, same energy level for the 2s, and same energy level for the 2p. Now what? So you know that 1s can only combine in this way, bonding, anti-bonding, sigma 1s, sigma 1s star, bonding and anti-bonding. And then the 2s could combine in this way and this way. The lower is a sigma 2s, the upper is a sigma 2s star anti-bonding orbital. But then we have some tricky scenario with the 2p. That's what we really have to focus on. So we got to imagine an XYZ Cartesian coordinate system, a three-dimensional, where this is the positive x, up here is the positive y, and into the board is the z. It kind of doesn't matter if I show whichever I show x, y, and z. I could go y into the board, z this way, whatever. But the point is, do you remember the p orbitals that it's called px, py, and pz because the two lobes lie directly on the px, the py, and the pz? So this boron has a px, a py, and a pz. And the next boron also has a px, a py, and a pz. So what does it all mean? When the px of one boron approaches the px of another boron, when they come at each other, since they're both on the x-axis, and if this is the coordinate system that I used, when they approach each other, this could be shaded and this could be shaded and it could be bonding, or this could be shaded, this could be unshaded, it could be anti-bonding, but specifically of what type, it's in the same line. They'll approach each other, one lobe will touch one lobe, and that'll be a sigma event. Now, it's got two more orbitals, so when we consider those, if it's on the py, and if it's on the py, how is that going to approach each other? They're going to approach each other in a parallel way, and it'll be a two lobe to two lobe do you see that this leads to a sigma? Sigma in the 2p. But this right here leads to a pi in the 2p. And that's using the y orbital, if that's how we set up our coordinate system. And then there's z. Again, this is x, this is y, this is z, according to my coordinate system. This is x, this is y, this is z. So if you go along the z, the pz, and of course, you know, they're not like diagonally, they're into and out of the board, right? Those p orbitals. So when they approach each other, again, it's going to be a parallel linkage where two lobes touch two lobes. And this is going to be, again, another pi 2p. So out of the p orbitals, there's 2px, 2py, 2pz for one boron. There's 2px, 2py, 2pz for the other boron. And when one of the 2p orbitals from each side link, it'll link in a linear way. And where the other two will link, they'll link in a parallel way. And when they link in that parallel way, they make pi bonds. So do you see from here, you're going to get one sigma and two pi's. See how you get a sigma and two pi's? And if you get one sigma and two pi's for bonding, you'll get one sigma and two pi's for anti-bonding. It turns out that a sigma bond is definitely stronger than a pi bond. Is anybody confused about this? This should be like relatively clear. A sigma bond is stronger than a pi bond. I often have students that remember something from Gen Chem, and when I say that, they're like, feel sketchy about it because they kind of remember the opposite. But it's not. It's not contradicting what you remember. We have to have some clarity. If you remember that a double bond is stronger than a single bond, you are correct. And if you remember that a pi bond is stronger than a sigma bond, that's incorrect. But often crossed. Often those circuits are crossed in the brain. To break a carbon-to-carbon sigma bond, a single bond between carbon and carbon, requires approximately 400 kilojoules per mole of energy. Here is something that should be very simple to understand. To break a bond requires energy. Forget that number for a second, but just to break a bond requires energy. That goes not only from all of Gen Chem, you should have learned that breaking a bond requires energy, because bonding releases energy, but from these orbital diagrams, you could remember when we did H and H, hydrogen and hydrogen. When hydrogens combined, they went to a lower energy state. That means they released energy. If a hydrogen atom and a hydrogen atom made a bond, it went to a lower energy state. And how do we break that bond? Do you remember we talked about enthalpy and entropy in the last lesson? To break the bond, we needed to put energy in to put one electron from bonding to anti-bonding so it would cancel out the bond. Please remember always, making a bond releases energy. To break a bond requires energy. To break this bond requires 400 kilojoules per mole of energy. Throughout this course, we're going to learn how much that is. It's a huge amount of energy. To break this, the entire double bond, the whole thing, requires approximately 700 kilojoules per mole of energy. What does that tell you? That the pi bond is weaker than the sigma bond. Which maybe from the pictures that we drew doesn't really feel right, because a sigma bond is where you have like one lobe and one lobe connecting, and a pi bond is where you have two lobes and two lobes connecting, so you think, isn't that stronger somehow? Two lobes and two lobes? But it's a much less of an overlap with the two lobes and two lobes versus one lobe and one lobe. When you have a carbon atom and a carbon atom sigma bound with p orbitals, let's say, it looks like that, where the p orbitals are heavily overlapped. And when a carbon and carbon are pi bound, it's only somewhat touching. So even though it's two and two lobes, it's like barely overlap versus completely holding on. So if the sigma bond is 400 kilojoules per mole, and the whole double bond is 700, then the sigma portion of the double bond is 400, while the pi portion is only 300. Do you see it's not as powerful, not as strong? So something about these diagrams is going to be bizarre. Just with the knowledge, how about this? Just with the knowledge that sigma bonds are tighter overlaps, that means lower in energy, more energy releasing, and with the knowledge that 3 of these p orbitals are going to mix with 3 of these p orbitals, 1 and 1 is going to make a sigma, and the other 2 are going to make pi, it should be predicted by everybody that when these combine, it'll make a lower sigma and higher pi. I'm not saying that's the right thing to draw right now, and don't necessarily draw it. I'm not saying that. I'm just saying that should be predicted. Do you see why? Do you understand why? If it makes, again, px, py, pz, right? If it makes a sigma bond and a pi bond and a pi bond, the pi bond should be equal because it's a px pi bond or a py pi bond or a pz, whichever. They're all p orbitals from the 2p. So they should all, whichever ones make pi bonds should be the same energy, but a sigma bond should be lower in energy. It's just, do you see how that's trying to be represented right here? But it's strangely not always so when orbitals mix. So there's certain things that I can't explain in this class. There's certain things we just have to like remember as a rule. And then hopefully somewhere in the future between this class, Orgo 2, biochem, maybe physical chem, maybe quantum chem, maybe inorganic chem, somewhere along the way, hopefully we get good enough explanations. So my goal in here is to explain everything, right? So like, how could I say that to you? How could I say there's certain things that it just can't be explained? The explanation is maybe requiring many parts. So like in Chem 1, you might learn that there's 2 ways that iron could become an ion, iron plus 2 and iron plus 3. It's never been explained to you why. Why not plus 1? Why not plus 20? In biochem, we're going to see that plus 4 exists. But only as a very short-lived reactive intermediate in a pathway. And then maybe mixing inorganic chem and physical chem, we'll start understanding the electronic states, the nucleus and all that, and then maybe understand why iron plus 2 and plus 3 are like the states that it could be in and not plus 1 and so on. So sometimes in the beginning you just have to remember. I'm trying to do everything I can to have you remember the orbitals, but there's something sketchy about the math of how these line up, and sometimes it's not what's expected. You expect sigma to always be lower than pi, but in certain scenarios here, the pi's are lower than the sigma. So we're just going to have to remember that when we combine this, for these elements, for things on this row, right now it's a boron-boron, but we could do a carbon-carbon, we could do a nitrogen-nitrogen, we could do an oxygen-oxygen, and we could even mix them. We could do boron-oxygen, or we could do carbon-fluorine. We could mix. What'll always be the same is the 1s and 1s. The way they combine bonding and antibonding will always be the same. The 2s will always be the same. The way they combine bonding and antibonding, the way the p's combine is a little bit strange. So sometimes they'll combine this way. Sometimes they'll combine in a 1, 2, 2, 1 kind of a way, meaning 2 of the p orbitals will make a lower sigma, slightly higher pi, and that means they'll have a antibonding pi, and then an even higher antibonding sigma. That makes a whole lot of sense, because the lower the bonding orbital, the higher and crazier the antibonding orbital is. It's like the more pushed down this is, its counterpart gets pushed up. So what will be weird is when it's this. When, kind of ran out of room, I'll draw it up here. When it's this. When instead of doing the 1, 2, 2, 1, 1 orbital, 2 orbital, 2 orbitals, 1 orbital, it goes like 2, 1, 2, 1. That's all sorts of bizarre, because even if this seemed like the correct way to line things up, why is it 2, 1, 2, 1 and not 2, 1, 1, 2? Do you see what I mean? Like, if the 2 go lower, then the 2 anti should go even higher, right? Very weird. And some books go to even explain that this seems normal, And then this is the weirdness, which is like, the hell are you talking about? This is the normal, by anybody's standards, this is the normal one. So we have to remember which one does what. Anybody read this and remember which ones do what? So the point of this group is to clarify things that you can't possibly really fully get on your own. The book demonstrates that if you have boron, boron, carbon, carbon, nitrogen, nitrogen, it's one of these scenarios. And then if you have oxygen, oxygen, fluorine, fluorine, neon, neon, it's the other one of these scenarios. Anybody know what I'm talking about? Anybody read it? I even asked you to do chapter 9. This semester's going to end poorly. You're all going to get like a 30 on your first exam. You will see that I'm not lying. I'm not trying to make you feel bad, nothing like that. By virtue of being in this room, you don't automatically just do well. You have to be prepared for the lesson. You have to come in already knowing stuff, and then we have to clarify it. If you come in not knowing anything, and I'm trying to feed you this, you'll only be able to recognize it on the exam, but you'll get it wrong every single time. The exam questions are not, can you recognize it? The exam questions is, how well did you master it, and what tricks can you overcome with it? You're going to see. You're going to learn the hard way, everyone here. It's unfortunate. But what I definitely won't do is lie to you. And I'm not lying now. Whether you took on too much, you're taking this with physics and calculus, whatever, nobody cares. The world doesn't give a shit. If you signed up for this, look, what my group can do is decrease the amount of studying, because the things that I'm going to be able to teach you, you'd have to do like 10, 15 hours of research to figure out on your own. But you still have to learn all of the basics that the book can teach you. That you need to do. There's no way around it. No way around it at all. So you should have already known this, because this is just clearly outlined in the book, which one of these it was. I even asked you to learn to read up ahead on this. It's kind of sucky. I feel bad for you. You guys are going to learn the very, very hard way. But then maybe you'll study for exam too. By that point, you lost the A for sure. You even lost the B+. You're going to be going on like a B-, C+. I'm saying nasty things. My group is upset. I could say nice things. It won't change the outcome. Go to a restaurant, they give you a dead rat on a plate, and then they say, here you go, in a nice way, right? The book says that if it's a boron, boron, carbon, carbon, nitrogen, nitrogen, B2, C2, or N2, it's this. And the book says that if it's an O2, an F2, or an Ne2, it's this. And it doesn't matter how many electrons it has, it's just that's the orbital distribution. So since this is B2, it's that one. It's a 2, 1, 2, 1. Sorry, why did I say that? It says 1, 2, 2, 1. It's sigma, then both pi's, then pi anti, and then sigma anti, right? That's what we have over here. Great. All of you are going to memorize that by an exam. Everything's awesome. You're going to come in. You're going to think you're prepared. And then on the exam, they're going to give you, professor's going to give you, draw the molecular orbital distribution for carbon monoxide. And then you're going to raise your hand and say, no fair. How do I know if it's this one or this one? Carbon is a 1, 2, 2, 1, and oxygen is 2, 1, 2, 1. And how am I supposed to know which one it is? See? So that's why we're here, for all the extra stuff. It turns out this is not just true for boron, boron, carbon, carbon, nitrogen, nitrogen. It has to do with the nucleus of the atom. That's what this whole thing is about. Where the orbital energy levels are has to do with effective nuclear charge. How much the nucleus is pulling on the electrons. So what is in common with all of these and versus all of these is the number of protons between the nuclei. And we could say there'll be a separation that that this kind of orbital distribution is for a sum of protons between the two atoms, a sum of those protons equal or less than 14. And this kind of 2-1-2-1 scenario is going to be for a sum of protons greater than or equal to 15. So where would carbon monoxide be? How would you distribute the carbon monoxide orbitals? Carbon has 6 protons. Oxygen has 8 protons. 6 plus 8 is 14. Now see, when a student doesn't study the orbital distribution, and then we have 10 more things to study, I'm just letting you know how this course is going to go, so that maybe we fix it by the next lesson. When you don't study things that I'm about to teach you, then you're trying to catch up. But this isn't the only thing we're doing today. We're going to get into nomenclature, we're going to get into constitutional isomers, and then it's going to feel overwhelming because it's going to feel like there's too many things to catch up on. You're going to forget the details. But the exam is all about the details. Every single question's on the details. So what's going to happen with the details is, I said sum of protons. You're going to look at the two atoms and you're going to count the electrons, because they're not even going to give you CO. They're not going to give you CO. They're going to give you CO cation. And then you're going to get confused between the electrons and the protons, and you're going to get the wrong orbital distribution and lose all the points. Do you know what the difference is by drawing this versus this? If it's a 10-point question, you lose 9 points. What if you miss an electron? You lose 7 points. Orgo isn't about, do I remember the idea somewhat? Orgo is, do I remember it absolutely perfectly? For little arrows and brackets, they take off 5 points, 7 points. You know what I mean? So like, you hear somebody got a 30 in Orgo, they must not know any Orgo. No, they basically know all the Orgo. They just got 5 points off here because they forgot an arrow. 7 points off here because they forgot an electron. We got to do way more than we're doing, whatever it is we're doing. So, I'm doing boron-boron. The distribution is 2p sigma, 2p pi, another 2p pi, 2p pi star, 2p pi star, 2p sigma star, because you see this is made out of 2p orbitals. It doesn't matter how many electrons I have in the system. This is still going to be drawn. Doesn't matter how many electrons. So this is going to be true for B2 or B2 plus or B2 minus. It doesn't matter. But once you draw the orbitals, then you fill in the electrons. Do you see what I'm saying? Like, I don't care how many electrons O2 has. It's still going to look like 1, 1, 1, 1, 2, 1, 2, 1. Does everyone understand what I'm saying? Don't mess up with like confusing yourself with electrons. Well, if it's O2, what if it's O2 cation? What if it's O2 anion? It doesn't matter. You'll draw the orbitals just like O2 anyway, then fill in the electrons as the last thing that you do. So now I'm up to filling in the electrons as the last thing that I do. I've got a boron and a boron. Boron has 5 electrons. So I'm going to fill in 5 electrons here. 1, 2, 3, 4, 5. And then I'm going to fill in 5 electrons here. 1, 2, 3, 4, 5. And then what did I say on how we fill this up? We don't look at where the electrons are over here. We just fill it up in the middle by counting the total electrons and working our way up. So 5 plus 5 electrons is 10. We start over here and we run our way up. 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Does the B2 molecule exist? The answer is yes. And what is the bond order? The answer is 1. And how did I get it that fast? Because this cancels by this, and this cancels by this, so you've got just those electrons that are not being canceled. 2 bonding electrons divided by 2, because there's no anti-bonding. Do you see? Or you could go 2 plus 2 plus 2, that's 6, minus 2 plus 2, which is 4. 6 minus 4 is 2, divided by 2, still 1 bond order. Do you see that? Sometimes professors ask really bizarre questions that shouldn't be asked. And nobody could answer them because it's just a random question that doesn't even make sense. Like they'll show you two compounds and they'll say which one's more stable. I can't think of a more bullshit question. Stable towards what? This entire semester we're going to be going through those questions, but not which one is universally more stable, but which one is more stable when reacting with water, which one is more stable when reacting with acid, which one is more stable, you know what I mean? Like it's in a case-by-case thing. You can't just say always which one is more stable. But when it comes to molecular orbital diagrams, there is discussion there on stability. If I say, draw the molecular orbital diagram of two things and tell me which one of them is more stable, the more bonds you have between things, the more stable it is, right? Stable means it's staying put, it's not moving, right? If I attach something to like the wall with glue, it bonds. If I attach something to the wall with crazy glue, it bonds more, it's more stable. Do you see what I'm saying? Like that's how we could think of bonds. More glue, more attachment. So if I show you two atoms and I ask you to draw the molecular orbital diagram, distribution diagram, and say which one is more stable, it just means which one has the higher bond order. Do you see how that kind of works out? But if I don't tell you in reference to the molecular orbital diagram, if I just show you two random molecules and say which one is more stable, stable in which way? Stable as a reactivity, internally stable, like which way stable? So it's like not a complete question. So if it's a question on a quiz or an exam regarding this chapter and they're asking which one is more stable, it's probably in reference to the molecular orbital diagram. But you might want to, let's say in a class, I think it's perfectly fair to raise your hand if it just says which is more stable. And it doesn't say draw the molecular orbital diagrams and discuss stability, you know what I mean? Which is more stable. I maybe would raise my hand and say, do you mean from like a molecular orbital perspective? Because that's not like a, you know, there's some questions that are like you can't ask on an exam. You know, like, what's the bond angle here? Professor, is this tetrahedral? Like, that's trying to ask for the answer, you know what I mean? When you say, do you mean by a molecular orbital perspective, that's not asking, is my answer right? It's like, do you mean within reference to this? It's, you know what I mean? It's clarifying the question. It's not asking you to say whether my answer is correct or not. So, a question would be, what would be more stable? B2 anion, or B2 cation? And you would draw the B2, you draw B2 anion, you draw B2 cation. It actually is easy to demonstrate without me redrawing. When I do a cation, what am I doing? I'm going to remove one of the electrons, and when I remove one of the electrons, the bond order will go from 1 to 1/2. And if I do a B2 anion, I'm going to add an electron. And where am I adding it? To a bonding orbital. So if I'm adding an electron to a bonding orbital, I'm increasing the bond order. Do you notice if I add electrons to the bonding orbital, I increase bond order? And when I add electrons to the anti-bonding orbital, I decrease bond order. So adding electron, now what if I take away an electron from a bonding orbital, I decrease bond order. And if I take away an electron from an anti-bonding orbital, I increase bond order. Make sense? So, with that being said, what's more stable, O2, O2 plus, or O2 minus? What's more stable, F2, F2 plus, F2 minus? What's more stable, N2, N2 plus, N2 minus? For homework, don't shortcut this. See what I did over here was a shortcut? If you all paid attention over here, I said, oh look, B2 plus, we're just removing an electron from here. Don't do that. For this, draw the entire molecular orbital distribution of O2, then draw another picture for O2 plus, then, because after you do 9 of these pictures, it'll just burn into your brain how to draw this. And that's what we want to do. We don't have enough practice to just burn it into our brain. You got it? So don't skimp on this. Take your time, draw it very neatly. The more effort you put into this, the more long-term you're going to remember it. And you don't have to do this in one sitting. In fact, don't do this in one sitting. do one of these today, do one of these tomorrow, do one of these, let's say, tomorrow night or the next day or something like that. And this way you spread it out over a couple of days and really keep it inside your head. How would we draw the molecular orbital distribution, the molecular orbital diagram for carbon connecting to oxygen making carbon monoxide? How would we do that? Carbon, look at this. Look at the subtle difference that we're going to do here. Carbon has a 1s orbital. Then carbon has a 2s orbital. And then carbon has 3 2p orbitals. That's nice. Oxygen has a 1s orbital, but careful where you draw it. Careful where you draw it. It's not drawn here. Let me make a dotted line just to demonstrate. Don't really make a dotted line because you have a notebook with ruled paper, right? So you could just go above or below the lines. But let's say this is the line that carbon's 1s is on. That's not where oxygen's 1s is going to be. Oxygen's 1s orbital is going to actually be a little lower. Why is that? Because oxygen's more electronegative, and electrons in oxygen's 1s orbital are lower in energy and closer to its nucleus. Does that make sense? And not only is that true for oxygen's 1s orbital, it's true for oxygen's 2s orbital. And not only is that true for oxygen's 2s orbital, it's also true for oxygen's 2p orbitals. Now I'm careful here. I'm careful to make sure that the 2p orbital for oxygen and the 2s and the 1s are lower than that for carbon, but nowhere near the wrong orbitals for carbon. Meaning, like, I didn't lower 2p so much that now it's closer to 2s for the other one, right? 2p for that is still close to 2p for this, 2s for that is close to 2s to this, to 1s, and so on, right? Now when I make a bonding, you'll notice that it's not equally distributed, the bonding orbital. Meaning that if I add these up, the bonding orbital will be closer to the energy of oxygen's orbital, which means the bonding orbital puts electrons sort of closer to oxygen, right? Isn't that a polar bond with electrons closer to oxygen? And the anti-bonding orbital will be sort of closer in energy and maybe closer physically, location-wise, to where carbon's orbital is. So the anti-bonding orbital will be closer to carbon and the bonding orbital will be closer to oxygen. This is going to be so important later on when we're discussing nucleophilic substitution, where something called the nucleophile is going to attack carbon's anti-bonding orbital. Why do we say carbon's anti-bonding orbital? Because the anti-bonding orbital of the bond is closer to carbon's anti-bonding orbital. Does that make sense? I'm going to take this dotted line away because it confuses the picture. I'm going to take this dotted line away. I'm going to take this dotted line away. Like if it's drawn, you'll see this is sort of closer to here and that's sort of closer to here. Same thing over here. The bonding is sort of closer to there and the anti-bonding is sort of closer to there. Make sense? And now what do we have? What do we have with the p orbital scenario? It is carbon, it is oxygen. You've got 6 and 8, 14. With 14, it does normal. 14 and less, it does normal. 1, 2, 2, 1. Normal. And not normal is switch the first two. So instead of 1, 2, it's 2, 1. Right? 1, 2, 2, 1, or 2, 1, 2, 1. So this is the 1, 2, 2, 1. You go all the way down. 1, 2, 2, 1. See that? 1, 2, 2, 1. Now that we've drawn the orbitals, you can put in it's a little tricky to draw. I'm not the best artist. I need these 3 orbitals to be lower than the p. I need this orbital to be higher than both of those s's. They shouldn't cross through each other, so it's a little sketchy. So kind of my picture got a little close, but whatever. I just fill in the electrons. Carbon has how many electrons? It's got 6 protons, 6 electrons. 1, 2, 3, 4, 5, 6. Do you see that? That doesn't sound so good. So that's 6. Oxygen has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. So now you have 14, and we're going to distribute them using Hund's rule and the Aufbau principle, bottom up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and I ran out of electrons. So if I have 14 electrons distributed over there, what is the bond order of CO? Now, CO is not in the book, but NO is in the book. How is NO going to be different than CO? It'll look exactly the same, except that'll be an N. Because that's an N, it's not going to have 6 electrons. It'll have 7 electrons. But overall, it's not going to be 6 plus 8. It'll be 7 plus 8, and 7 plus 8 is 15. So because it's 15, it's not going to be a 1, 2, 2, 1. It'll be a 2, 1, 2, 1. Overall, the bond order is really not going to be different, but it's weird. It demonstrates that in those cases, because of the nuclei and whatever, the p orbitals, the pi orbitals, are lower in energy than sigma orbitals, which is not expected. We think sigma Zoe should be lower than pi, but in these cases, pi is lower than sigma. Weird, but true. So what's the bond order here? This gets canceled, and 3 bonds don't get canceled. Do you see that's 3 bonds? You see it has electron pair 3. So the bond order is 3. The bond order is 3. The bond order here should match the bond order you get from the Lewis structure if you draw a proper Lewis structure. If we draw a proper Lewis structure of carbon monoxide, how do we draw a proper Lewis structure of carbon monoxide? You draw the letter C, you draw the letter O. I hope you guys learn and listen and practice. I've got students now in Orgo 2. We don't really use the Lewis structure I'm about to draw so much in Orgo 1. We just draw a line bond and whatever. Then comes Orgo 2, and it's assumed you remember everything that we've done. Students in Orgo 2 right now are having trouble because having issues drawing Lewis structures. It's so sad. You draw a carbon, you draw an oxygen. Then what? You put a stick between them. Carbon has how many valence electrons? 4. Oxygen has how many? 6. 4 plus 6 is 10 electrons in total, minus the 2 that we've used. That means we have 8 electrons. This is exactly how we have done things from day 1. We have 8 electrons left to place. Who do I place them on, carbon or oxygen? We always say put them on the outer, which is outer. There's no outer. Put it on the more electronegative. That's the smartest thing to do. So 2, 4, 6, 8. What's the problem with this Lewis structure? Carbon's octet is broken, right? We want to complete carbon's octet. Carbon has 2 4 electrons around it, so it needs 4 more. That means you're going to bring in a pair. That means you're going to bring in a pair. And carbon monoxide's Lewis structure looks like that. And the bond order is 3. Do you see? Which matches the bond order of carbon monoxide in the molecular orbital picture. Everybody with that? Carbon monoxide's a very interesting little beast. Here's what makes carbon monoxide interesting. If you finish during the Lewis structure, we have to put in formal charges, right? What's the formal charge of carbon? It's 4 minus 1, 2, 3, 4, 5. 4 minus 5 is negative 1. This is 6 minus 1, 2, 3, 4, 5. 6 minus 5 is positive 1. So carbon is negative and oxygen is positive. So who cares? Why is that interesting? Well, clearly it doesn't look stable because it's got charges across a bond, but here's how things get worse. Ignoring formal charge, which atom is more electronegative, carbon or oxygen? Oxygen. And that means there's a polar bond. And if there's a polar bond, we say that this is partial negative and this is partial positive. So which is it? Which is it? Is it negative or is it positive? Is it positive or is it negative? The formal charge and the partial charge distribution say opposite things. Very weird. In reality, it's partial negative and partial positive. Formal charges is just for us in orgo to use for reactions. So we're going to be using them later for reactions. We'll deal with that later. What's your question?
You said that the lower energy, like sigma orbital, will be closer to the more electronegative
Yeah.
element. Is it also supposed to be like that in the 2p energy
Yeah.
level? Okay,
Yeah.
because I couldn't tell by the...
Yeah, it's like the drawing doesn't really look great, but if you look in books, like if you see something like that, it'll be
It will be significantly...
like that.
Yeah.
I don't mean like you draw this shifted to the side so much. It's just the energy is closer to here and the energy closer matches here. And that actually gives you the understanding of like what a polar bond is. If the electrons over here are being shared between these two, this orbital has more of the quality of this orbital. They're being not shared equally. They're being shared more by the orbital that has similar quality and not the orbital that has less similar quality. True or false? True or false? A bond order must be an integer. Okay, let me define the word integer. It's a whole number. It's not a fraction. An integer is like a 1 or a 2 or a 3 or a 4 or 5 or a 6. False. We've seen half orders. Seen 1.5 orders. And it turns out for resonance, you're not going to have full bond orders. You're going to have half bond orders. When it comes to resonance, this isn't a picture you could draw. Resonance has its own delocalized molecular orbital diagram. This is the regular molecular orbital diagram. Resonance has its delocalized. There's one picture of this in chapter 1. It's figure 1.19, if I remember correctly. And if time permits, I'm going to explain it because it's something really a topic of Orgo 2. So I might explain it before the exam, let's say. It's got a low chance of ever popping up now, and it was just for demonstration purposes in this chapter, and really a topic from chapter 20. What if my professor puts that on the exam? Okay, what if your professor puts something from chapter 50 on the exam? Right? The book only goes up to chapter 29, but your professor could put something from chapter 50. Do you know what I'm saying? Like, we're not going to look for the future. We're going to look for now. So how would this look different if it was CO plus? You'd lose a bonding electron. The bond order would be 2.5. What if it would be CO minus? Kind of impossible. Because then there would be more than an octet for both atoms, right? Oh, unless you broke it up into radical anion, right? I'm getting close to finishing this chapter, so, well, except for the dipole stuff, but I'm not going to teach you the dipole stuff in this room. I'm pretty sure I already sent you an email to look at a particular video. Did anybody watch that video on the dipole stuff? So you've seen the vectors from physics, right? The rest of you who didn't, watch that video. It's not only important because it interconnects with physics, it's what we're going to have to use to understand later in the semester anyway. We're going to have to be able to look at a molecule like this and explain why it's polar or not polar or so on, or like this. And the way the book does it and just shows arrows in random directions without actually using vector analysis is not the right thing to do, because the book shows simple. The book's vector analysis works for those simple 3 examples. Try to do that with any other example, you can't make sense, can't make heads or tails out of it. So we get into now hybridization. Because so far the orbital diagrams that we've drawn, they weren't hybridized orbitals. They were just regular unhybridized orbitals. An S and an S make a sigma bond, a P and a P make a pi bond or a sigma bond. But now we get into hybrid orbitals. And when I first tried to study this, I was not a great student always, but when I started trying to become a good student and trying to learn, I abandoned asking questions like what's on the exam, and I just tried to learn the topic. I'm reading about this, and I'm like, I started giggling. I'm like, this is such bullshit. Like this entire thing, and it isn't. But the long story short is, it's not bullshit. But the first time you kind of hear what Linus Pauling's idea is, you're like, how is this even science? This is just like a complete cop-out. So, hybridization, the theory of it, was developed by Linus Pauling. I mean, he came up with the theory of bonding in the first place. A lot of people never heard of Pauling. You heard of his work. So, and if I mention the name Pauling, you probably get it confused with Pauli. Pauli's exclusion principle. But Pauling has nothing to do with the exclusion principle. Linus Pauling was quite a remarkable scientist. And he came up with the whole idea of electronegativity. He came up with the whole idea of hybrid orbitals, sp2, sp3, sp. Linus Pauling was one of 4 people in all of history to win 2 Nobel Prizes. That's impressive. More impressive is he was one of only 2 people to win 2 Nobel Prizes that are in different fields. Now that is mind-blowing because, look, you could be the world's best swimmer and win Olympic gold this year, and then you could come back 4 years later and still win because you're just that good. You know, like Mike Tyson was the best boxer, so the fact that he kept winning was like, well, yeah, he's the best boxer. But imagine Mike Tyson was the best boxer and then also won some literature award and then also invented the cure for cancer. You're like, how the hell did he have time to be the best in every field? Marie Curie won the Nobel Prize in chemistry and physics, which is just like, holy shit. Not only did she show off in chemistry, she went and showed off in a whole different discipline, physics. But they're both mathematically related, right? So, like, I'm not taking anything away from her skills. It's crazy, but, like, chemistry and physics, nowadays there's a blurry line between them. High-order research in chemistry might be physics, and advanced research in physics sometimes is chemistry. You go and look at most physics papers published, that they're talking about the atom or something. So, Linus Pauling won 2 Nobel Prizes. One was in chemistry and the other one was in peace. He wrote essays against the war and somehow ended up with a Nobel Prize in peace. So that's like even crazier. Not taking anything away from Marie Curie. She should have maybe won 4 Nobel Prizes. The fact that she was a woman at the time, they didn't even want to give her her own prize. They had to make her share it. So can't take over. Maybe she would have won the most Nobel Prizes if she was alive now and doing her work now and got Nobel Prizes now. But still, to have those radically different fields, like peace versus chemistry, impressive dude. He was also very against the vitamins. So the smartest people in the world sometimes have bizarre quirks. For example, Albert Einstein married his cousin. Did you know Albert Einstein married his cousin? It wasn't just his cousin, it was his first cousin. When she married him, she didn't have to change her name because her last name was Einstein. Do you understand? Like, that's horrible, you know? Like, smart, very smart people have some bizarre features, right? Linus Pauling had like this big, like, I don't even know what to call it. He was like a superstition or something. He thought that chemical companies, he thought that vitamins are complete bullshit and that chemical companies were packaging extra stuff that they had left over. Like at the end of the year, we sold that chemical, we sold that chemical. We have a kilogram of this chemical left over. We had like 5 grams of that chemical left over. Let's just slap it all together in a pill and say, you guys need to eat this to be healthy. Like that's how far he took it. He was a bit of a biochemist in his later years, so maybe something he said was right. I don't know, but it felt like really like paranoid, like what he was saying about vitamins. What did he say about hybridization? This blew me away when I first learned it. He said, this is weird. He said, we have to investigate this. When you look at carbon connected to 4 hydrogens, when you look at methane, does everybody know this is called methane? When you look at methane, every single bond is identical. The bond between carbon and this hydrogen is no different than the bond between carbon and that hydrogen. The bond order is the same. Not only is the bond order the same, the bond strength is the same. If I want to break this bond, it's the same strength as breaking this bond. And that's weird. You would think, why is that weird? Well, let's take a look at carbon's orbitals. What orbitals does carbon use? What is carbon? Carbon's electron configuration is 1s2, 2s2, 2p2. This, of course, is the noble gas core, and this is its valence electrons, right? Like if I draw the distribution of electrons, remember this in Gen Chem? 1s, 2s, 2p. So it's got 2 electrons in the 1s, 2 electrons in the 2s, and 1 electron in each of the 2p orbitals, right? So now maybe you should start thinking of, this is bizarre. If carbon is using these electrons to make bonds, and it's making bonds to 4 different hydrogens. Let's look at carbon's Lewis structure. Carbon's Lewis structure is dot, 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 right? Now these dots are its valence electrons, so forget about that. 2 of these dots are 2s orbital dots, and 2 of these dots are 2p orbital dots, right? This doesn't even look like it matches to this, right? Doesn't this look more like 2 dots in the 2s and then 2 separate dots in the 2p? Like, at least that's what it's sort of telling us. Do you see that? That's not how we draw it, but that doesn't matter. Do you see there's like a difference in the 2p and the 2s? And if carbon was going to use a 2p electron to make a bond to a hydrogen, wouldn't it be a different distance than if it used a 2s electron to make a bond to the hydrogen? Look, I'm carbon, and I have a 2s electron that's close to my nucleus, and I have a 2p electron that's further from my nucleus. And if I grab a hydrogen this way and I grab a hydrogen this way, how could they be at same lengths? Isn't one going to be closer than the other? I'm using different electrons. It's in this kind of an orbital versus that two-lobe kind of an orbital. So Linus Pauling is looking at this and saying, this is weird. How could it be that they're the same when they're not the same? He comes up with this theory of hybridization, which just seems like the biggest cop-out. He says that when carbon is on its own, it's got a 1s2, 2s2, 2p2, the orbital distribution that I showed you. But when it goes to bond, it mixes and all the orbitals become the same. Like when I read that, I'm like, right away, later on, years later, because after a little while I understood this, but at first that just sounded like, okay, so you're telling me they're different, but when it bonds, now they're the same. How could that be like an answer to anything? That was like Stephen Hawking's explanation for black holes. Did we all hear who Stephen Hawking was? Right? What's the issue in physics with a black hole? In our universe from chemistry, matter can't be created or destroyed, correct? But anything that goes into the black hole disappears forever. Do you see the black hole is a paradox with our universe? Like physics disappears in a black hole somehow? So Stephen Hawking held a press conference once. This was like, when I watched this conference, I started giggling. I'm like, this is the Linus Pauling cop-out, it felt like. He held a press conference, he said he solved the physics dilemma of a black hole. And I thought it was going to be this crazy math. And what it was this. He said, we all now believe, all physicists believe, in multiverse. Meaning there's not just one universe, there's an infinite number of universes. Right? So, that means that some universes have black holes, and some universes don't have black holes. So as time passes, the black holes in the universes that have black holes, those black holes will swallow up the universe. And for the universes that don't have black holes, they will stay. So it doesn't matter. Do you see how that doesn't solve the dilemma? Do you see that's like, I don't know, I felt like, thanks, but that's a cop-out. Like, how does physics break in the black hole? Not that it doesn't matter. Like, the whole press conference, it doesn't matter. To me, it's like, how is this possible? They're different? No, don't worry. When they go to bond, they're the same. It feels bizarre. But whether we understand how they do that, it actually turns out to lead to lots of important properties. So here's a regular carbon atom. Let's say this is a regular carbon atom. You're going to need like the width of the page, because I'm going to draw a carbon atom. And then I'm going to draw a carbon atom when it looks like this. And then I'm going to draw a carbon atom when it looks like this. And then I'm going to draw a carbon atom when it looks like this, for example. What's a regular carbon atom? It's got 1s2, 2s2, 2p2, right? The s orbitals and the p orbitals, like we said. So I'm showing the valence. Over here is going to be a 2s orbital, and somewhere higher up is going to be 3 2p orbitals. And carbon is going to have 2 electrons in the 2s and 1 electron in 2 of the 2p's. Right? Right. But he says when carbon is like this, when carbon is bonded to stuff, those orbitals mix and they all hybridize, sort of like taking resonance contributors and averaging them out. So if I average out 1, 2, 3, 4 orbitals, I'm going to get 4 of the same kind of orbitals. See, I used 3 of one type and 1 of the other. There's 4 altogether. Going to mix them and get 4 of the same type of orbitals. But here's where they're going to be. They're going to be somewhere over here. And before you draw this in your book, understand why. Understand why. If we give this math, we'll give this a mathematical thing. Let's say the 2s orbital has a height of 5. And let's say this has a height of 10. That's bad numbers. Let's say this has a height of 1 and this has a height of 2, right? If there was one of these and one of these, then it'd be 1 and 2, and right in the middle would be 1.5. But because there's 3 of these and 1 of these, it's 75% like this and 25% like this. Do you see it's not in the middle? The energy is not in the middle, but 3/4 of the way up. That makes sense? Let's take any numbers and say, like, it's like 1 plus 2 plus 2 plus 2 divided by 4, and it'll be way closer to 2, the answer, than it'll be to 1, right? So you have 4 equal orbitals that are closer to what the energy is of the 2p, and these orbitals are sp3. We already said that if you have 4 things, it's sp, pp, sp3, right? And you have 1 electron distributed in each of them. And that's great, right? Okay. So what? What happens here? Now I'm going to draw the other carbon right here. I'm going to draw this other carbon and another bond set and another carbon, another bond. But really, the orbital that is going to be here is not the orbital of the bonding state. It's just going to be 1 carbon's orbitals, right? What do we have here? What is the hybridization of this carbon? The hybridization of this particular carbon, it's got 1 domain, 1 domain, and 1 domain, 1, 2, 3. It's sp2, meaning that the s hybridized with 2 of the p orbitals and not the third one. The third one was just left out. So if the s hybridized with 2 p orbitals, the result is not going to be that high. It'll be a little lower. 1, 2, 3. And then you're going to have the p orbital where it originally was. Does that make sense? If we think of this as a number line, this is at position 0. Look at even, let's just do this math. Let's call this a 0 point. This is at the bottom, 0, and this is 10, right? 0 plus 10 plus 10 plus 10 divided by 4, right? It's 30 divided by 4, right? What does that come out to be? 7.5, right? So it's not at 5, it's at 7.5. But if we're doing that, if we're doing sp2, then it's not 0 plus 10 plus 10 plus 10. It's 0 plus 10 plus 10 divided by 3. It's 20 divided by 3. And that's a little less than 7. So this is 7.5, and that's like 6.9 for sp2. Do you see that? And then the last one is going to be the easiest one to really explain. This carbon is an sp hybridized, right? That means it uses 1s and 1p. And what is that? What's the result of that? Isn't that going to be smack in the middle? 50% s and 50% p right in the middle? So that's going to be like right over here, sp. The other orbitals don't disappear. That's one of the most important parts. The other orbitals don't disappear. So you have 3 orbitals that are hybridized, sp2. And that means you have 1 orbital that was just an original p orbital that didn't do anything. It didn't hybridize. And over here you've got 2 orbitals that hybridized, an s and a p. That means 2 of the remaining p orbitals didn't do anything, didn't hybridize. Are you with me? Is everybody in the room with me? If you got 4 orbitals, s, p, 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 and you hybridize the sp, you still have p and p left over. Like let's say the sp2 is s with px and py. That means the pz didn't hybridize, so this is still the pz. And here maybe it's the PZ and the PX, or the PZ and the PY, or the PY and the PX. Whatever two didn't hybridize, they stay. Now here you're going to distribute one electron in each and then have one electron up there. Here you're going to distribute one electron in each and have one electron and one electron over there. The point is now, if you've got 4 equal electrons in sp3 orbitals, you're going to have 4 equal bonds. If you've got 3 equal electrons in sp2 orbitals, you'll have 3 equal bonds, but then that is going to do something else. This 2p orbitals electron is going to do something else. And over here, if you've got 2 electrons in the sp orbitals, you could have 2 equal bonds between the sp orbitals, but then these 2p electrons are going to be doing something else. Putting the story together with hybridization and also the way that bonds happen, where it's a p orbital going like this with another p orbital to sigma, or a p orbital going like this, the way the pi bond is made, Lewis structures start making sense. For example, what does this look like right here? What does this molecule look like? This is a sigma bond, this is a sigma bond, this is a sigma bond, this is a sigma bond. What do you have in between here? You've got a sigma bond and you have a pi bond. We're all there, right? How do you make a pi bond? To make a pi bond, you need a p orbital and a p orbital to overlap like this, right? What's the hybridization of this carbon? It's sp2, but every carbon has an s and 3 p orbitals. So if the hybridization of this carbon is sp2, then it's got a leftover p orbital with an electron in here. So this carbon's got a leftover 2p orbital that has an electron. What about this carbon? What's that hybridization? It's also sp2. And if it's sp2, then it's got a leftover 2p orbital with an electron in there. And the leftover p orbital and the leftover p orbital, can't they overlap in this kind of parallel way and make a pi bond? Do you see how we can start drawing pictures of this? What's the hybridization of this? It's sp, right? And because the hybridization is sp, that means it's got 2 p orbitals left over. Question, how many pi bonds are there? The answer is 2. One of the p orbitals is making a pi bond, and the other p orbital is making a different pi bond. Do you see how that works? That's not just the only thing that hybridization is going to be helping us with. When I first learned this, I was like, this seems like a funny little way to just get around the fact that you've got different electrons in the beginning, and then if it's bonding, they're the same types of bonds. But this predicts something. This predicts that electrons in an sp orbital are more stable. And this predicts that electrons in an sp2 orbital are less stable. And it predicts that electrons in an sp3 orbital are even less stable. We could think of this as not just energy, but distance from the nucleus. You all paying attention? The s orbital is going to be closer to the nucleus. Imagine the bottom of this board is the nucleus. The s orbital is closer to the nucleus. The p orbital is further from the nucleus, right? So the sp3 orbitals and the bonds that it makes is further from the nucleus than the sp2 orbitals and the bonds that it makes. And the sp2 orbitals and the bonds that it makes is even further from the nucleus than the sp. See, in Gen Chem, you may have learned that a triple bond is shorter than a double bond, and a double bond is shorter than a single bond. Raise your hand if you've learned this. As a student, I learned that too, but when I learned it, I thought it meant something, and it didn't mean that. The book only says that the triple bond is shorter than the double bond. It never says why. And I invented in my own brain the reason that it's shorter, a triple bond is shorter than a double bond, is because there's more bonds, so more connections. But that's not it. It isn't because there's more sticks. It's because the bonding orbital that's being used between carbon and the other carbon is sp orbitals. Look at what this picture is saying. I hope we're not tired and didn't sleep last night. If we are, try to tune in right now. If this bottom of the board is the nucleus, the sp is electrons closer to the nucleus than sp2. and that's closer than sp3. Let me draw it like this. If I have a carbon and it uses an orbital called an sp, the electrons in that orbital are closer to the carbon than an orbital that's sp2, which is closer to the carbon than an orbital that's sp3. So imagine I have a carbon linked to another carbon, and they're using sp3 orbitals. Do you see you'll have a carbon with a big orbital and another carbon with a big orbital, so the carbons will be far apart? Versus carbon with an sp orbital and a carbon with an sp orbital, and they'll each be closer to each other. Do you see what that predicts? And you know why that's an important prediction? It wasn't just me. It wasn't just me who thought, oh, if triple bond is shorter than double bond and double bond is shorter than single bond, it just must be because there's more bonds. It wasn't just me that thought that. That's a logical thing to think. Scientists, physicists, chemists thought this. And Linus Pauling comes along, makes up this hybrid orbital theory, and from the hybrid orbital theory, it predicts that that's not the answer. Now, how do you find out if that's the answer or not the answer? Because how do you know whether it really is because they're hybridized and sp looks more like the lower one than sp2? Do you see sp is closer to where s is than sp2? How do you know it's that, not this? I need you guys to follow the story here so I could show you why we know for sure. The story is, while this makes sense that if sp is really 1s and 1p, that means it's 50% p, 50% s, and it's closer to the s energy level and distance than sp3. Well, that makes sense. How do you prove that the reason the bond is shorter is not the number of bonds, but because of the type of orbitals you use? How do you prove that? And the answer came here. In looking at the bond length between carbon and hydrogen. In this kind of a compound, looking at the bond length between carbon and hydrogen in this kind of a compound, I'm going to point at the bond, and looking at the length of this bond in this kind of a compound. Follow the logic. Try to follow the logic here. This should be interesting to you. This is the only way to do orgo, I promise you. Everyone that does well just lets themselves not like worry, is this going to pop up on the exam, but find the story interesting. So when you find the story interesting, you could repeat it to somebody. You want to tell them. You want to like be like, oh, this is how it goes. And if you don't find the story interesting, it's impossible. If it was the number of bonds and not the hybridization thing, then this bond right here, and this bond right here, and this bond right here would be the exact same length, because it's one bond between hydrogen and carbon, it's one bond between hydrogen and carbon, it's one bond between hydrogen and carbon. But if it's the hybridization thing, then they wouldn't be the same length. Because what kind of orbital does hydrogen use? Hydrogen always uses a 1s orbital. That's the only orbital it has. It's a 1s orbital. But in this case, it's a connection between hydrogen's 1s and carbon's sp3. That's the connection. And here it's a connection between hydrogen's 1s and carbon's sp2. And here it's a connection between hydrogen's 1s and carbon's sp. Do you see, if hydrogen is a sphere that links to an orbital from carbon, the longer orbital from carbon would make a longer distance between hydrogen and carbon. And the shorter orbital from carbon would make a shorter distance from hydrogen and carbon, if it was the hybridization thing, and not the number of sticks. Well, they measured it. And it turns out that is the shortest carbon to hydrogen bond. That's the next longest carbon to hydrogen bond. And that's the longest of all carbon to hydrogen connections. Which means it's not the number of bonds, but just the hybridization. Do you see how that works out? We're going to need to use this. This isn't just random. It doesn't matter if your professor taught you this. It doesn't matter if your recitation instructor went over this. We're going to need to use this in one of the toughest chapters, chapter 4. We cover acid and bases. We're going to need to use hybridization to explain why the pKa of an alkyne is 25, while the pK of an alkene is 40, while the pK of an alkane is above 50. It's not just random numbers I'm using here. We need to understand the theory of why. So, and my students do. My students remember this. So I know It's taking forever to get out of chapter 1. But just because some other professor could be in chapter 5, let's say. Last semester actually was way worse than what we got going on right now, no matter where your professor is. I had 2 students in my group that were from a different school, PACE. And their professor wrote the book that they were using, and their professor decided on what was important in the book and not important because the person wrote the book. So in the first week, they started 2 weeks after my program started. So they're barely studying because they're like, my class didn't even begin yet, right? So after 2 weeks, we're still in chapter 1, and their school didn't even begin yet. They had the first lesson. It was like a Tuesday. The professor covered chapter 1 and 2. Then came Thursday. The professor did chapter 3, 4, and 5. By Saturday, they're 5 chapters ahead of us. That's way worse. That's way worse than whatever position we're in right now. However far behind, we're way better than them, right? So like, we caught up. We were fine. By the semester, we were fine. We just can't skip on anything. You have to solidify all these ideas. Every idea connects to every next idea. And we're going to exemplify this in a second. You have a question?
Can you repeat what you said about how the sp3, sp2, and sp orbitals, about the stability? You said that.
Yeah, so the stability, when you say the word stable, you're exactly saying something about energy. Something that's saying something is stable means it's low energy. Something that's unstable means it's high energy. This is just what it means as a general word for stable. When you're asking which one of these molecules is more stable, that's a little bit rough to ask because then you have to ask in which reference frame. Which is more stable in terms of a reaction? Which is more stable in terms of what? How it moves? Which is more stable in which way? Which one's more stable in a reaction is which one is not reacting so much. Which one is less stable is which one is reacting more. Less stable, reacting more, it's more energetic in the reaction, right? So like stability and energy is the same kind of a thing. You'll notice that as we go this way, you go lower in energy. So that means the electrons there are closer to their Earth, closer to their nucleus, more stable. Let's see if we can take what we just learned and apply it. Raise your hand if you're going to get this answer right. One hand. Rank these carbon-to-carbon bonds from the shortest to the longest. So you're going to write this, 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 this. Here you're going to write shortest. Here you're going to write longest. And you will fill in A, B, C, and D in there. Shortest, longest. So in ignoring everything that I've said, you can say A is the shortest, then comes C, and then B and D are the same length because you're looking at single, double, and triple, and that has nothing to do with anything, and that's the wrong answer. Or we can do what we've just learned and learn that the sp is a shorter distance to the nucleus, and the sp2 is a longer distance to the nucleus, and sp3 is a longer so therefore, A is a connection between sp and sp. B is a connection between sp and sp2. C is a connection between sp2 and sp2. And D is a connection between sp2 and sp3. When you write it that way, does it become obvious which one's the shorter one and which one's longer? An atom with an sp orbital has electrons closest to it. So if two atoms with sp orbitals connect to each other, then they're closest to each other. sp and sp is the closest to each other. Next is not sp2 and sp2. Next is sp and sp2. In fact, they are in order. We're going to be discussing percent S character. So on the hybrid orbital picture that you drew, right? Go back a page or whatever in your notes. The one where I saw carbon, I drew a line, and then the other carbon, right? The p orbital, the s. The one that was sp3, with all those four equal orbitals, you could say that this hybridization is 75% P, 25% S. It's such an easy math thing to do. There's four orbitals. One of them is S. So doesn't that make it 1/4 S and 3/4 P? The one that's sp2, is 67% P, 33% S. Does that make sense to you? And the one that's sp is 50-50. 50% P and 50% S. So here's the point. Remember how we did the picture of what an s orbital is? Remember the wave function, all that? In an s orbital, the density is right closer to the nucleus. That's an s orbital. In the p orbital, let's say it's the px, py, pz, doesn't matter. It looks like this, where the density is more of a distance from the nucleus. So S means closer to the nucleus. And any hybrid orbital that's got a bigger percent S means that the electrons are closer to the nucleus and more stable. Right? So this has electrons closer to the nucleus and more stable because it's 50% S. Then it's this one that's 33% S. Then it's this one that's 25% S. You follow this? What I want to do is draw a diagram for these molecules. This is not so much going to be important for any exam right now. This is going to be something that's important in a week or two, 3. Definitely in like a month when we do substitution reactions. You absolutely need to know shapes of everything. So I want to draw what methane looks like from an orbital diagram. Not a molecular orbital energy diagram. That's how we drew S and S and combined them sigma, sigma star. Not that energy diagram. But just a bubble picture. The textbook has these with like red and blue balloons, it looks like. You've seen these pictures. We want to be able to draw every one of them because that's going to give us an idea of shape and resonance and so on. It's not very difficult to do. What's the hybridization of this carbon? sp3. So you draw a carbon, and you're going to draw, now I should say, an sp3 or sp2 or sp looks like this. If you have an S and you mix it with a P, so I'm going to show you like how we develop it, and then I'm going to show you what we actually draw. First, how we develop it. If you mix an S with a P, or if you mix an S with a P and another P, or another P. This would be sp3, this would be sp, right? The S could be shaded or unshaded, and the P obviously has one side that's shaded, right? If these mix, that means the shaded part and the shaded part combine and give you like a bigger shaded part. So the orbital would look like a small lobe and a big lobe, and this would be the lobe that's doing the bonding. And then the smaller side lobe would be the anti-bonding lobe. So the same thing here. Let's say this is unshaded, and then you have a shaded, and you have a shaded, and a shaded. The unshaded would combine with the unshaded, and carbon would have like a big unshaded and a small shaded, and this would be the bonding side, this would be the anti-bonding side. So the anti-bonding side is going to be 180 degrees away from the bonding side. To not confuse the pictures, we don't ever really draw the anti-bonding side. So I showed you how it's developed. Now I'm going to show you what we actually draw. We don't shade anything. We just draw what looks like half a p orbital, like almost like a teardrop. If I want to draw a carbon with an sp orbital, I just draw that. If I want to draw a carbon with an sp3 orbital, I just draw that. There's no distinction in shape or size when I draw sp, sp2, or sp3, even though we know that sp is closer to the nucleus and sp3 is further from the nucleus. If I draw that, it could be an sp, an sp2, or an sp3. It doesn't matter. So how do you know if it's an sp, sp2, or sp3? Based on how many of them you draw. If it's sp3, there's 4 of them. It's tetrahedral. If it's sp2, there's 3 of them. It's trigonal planar. If it's sp, there's 2 of them, right? So going over here. If I want to draw this carbon is sp3 hybridized. That's what this carbon is. I'm going to draw 1, 2, 3, 4 orbitals. I'm trying to draw that as tetrahedral as possible. Do you know what a tetrahedron looks like? Every angle is 109.5. 2 of the bonds are in the plane of the board. And 2 of the bonds, one of them's out of the board, one of them's into the board. Have you seen this picture in the book yet? This perspective picture. 2 of the bonds are in the plane of the board, and one bond is a dash that disappears, meaning goes into the board, and the other one's a wedge. The wedge, it's not a triangle, it just means it's growing. That's why it looks like this, right? And you always have to draw it. It doesn't matter where you draw the bonds in the plane of the board, but do you notice that the bonds in the plane of the board go one way, and the wedge dash go the other way? So for example, if I start drawing a carbon and I do this, and I draw a stick this way, right, as one of the bonds in the plane of the board, I have to draw one more bond in the plane of the board. Where am I going to draw it? I have an option. I could draw it up, or I could draw it this way. Why? Because there has to be like an angle between it, right? I could draw it up, or like I said, I could draw it this way. This is unacceptable. Now that I have the 2 sticks in the plane of the board, I need to draw the wedge and dash. If the sticks go this way, the wedge and dash go the other way. So I could draw a wedge and a dash. Do you see if the sticks go down, the wedge and dash go up? Really simple. Now when we draw the sp3 picture, we're drawing bubbles instead of sticks, wedges, and dashes. So if I draw a bubble up and a bubble this way, I'm going to draw a bubble forward. I have to try to draw a bubble back. So this is my attempt at a bubble forward and trying to draw a bubble back. Right? You'll get used to it by the 3rd picture. By the way, none of this is orgo. This is all just tedious Gen Chem review. And unfortunately, it's what we have to do. You can't imagine how badly I don't want to do this. You can't imagine. I've taught this 100 times already. That's not an exaggeration. I teach this like 5 times a year for the past 15 years. I've done this way too much. But it's necessary. It's incredibly necessary. So therefore, I need you to be as enthusiastic as possible. Orgo turns on after a couple of chapters. Orgo really begins in chapter 4. Before chapter 4, Orgo is just like, it's like taking a painting class, and your teacher is showing you, this is a chisel, so do this chisel stroke. And you're like, when am I going to make a picture? And it's just like, why am I standing there doing a chisel stroke? Okay, here's a fan brush, just do this all day. It's boring. It's like I'm doing this all day. Then suddenly you have to paint a landscape, and then in that landscape you have to do this, you have to do that, and suddenly it all comes together. When it all comes together, it starts becoming interesting for everybody. Until then, I'm going to try my best to make it make sense and be interesting, but till chapter 4, it's not interesting. It can't be. There's just rules we have to do. This carbon's sp3, I drew its 4 sp3 orbitals. And now I have to draw it bonded to hydrogen. A bond is when an orbital overlaps an orbital, whether it's a p orbital overlapping a p orbital this way, a p orbital overlapping a p orbital, or overlapping the orbital, right? So that means, what's a hydrogen look like? What's a hydrogen look like? A hydrogen has an s orbital around it. So you draw the letter H and you put a sphere around it, because that's the way that s orbital looks. So here is a hydrogen with an s orbital. So the bond would look like this when this orbital overlaps that orbital. So you would draw a hydrogen outside of this orbital and then put a sphere around it in a way that those two overlap. Do you see? Here is what a picture is going to look like for a student that didn't study and tries to cram this in their head the day before the exam. They're going to draw a carbon and then just draw a bunch of circles, not even going anywhere, and put H's inside there. So now they drew hydrogens inside carbon's orbitals. Right? A bond is a marriage between a hydrogen and a carbon. It's like them holding hands. It's not putting your hand through the other person's hand. That doesn't work. Physics doesn't allow this. Here is a bond between carbon and hydrogen. Here is carbon's orbital. You don't put hydrogen in that orbital. There's electrons in that orbital. And those electrons combine with electrons in hydrogen's orbital. So you put a hydrogen outside of there and you do that overlap. You put a hydrogen outside of here, you do that overlap. You put a hydrogen outside of here, you do that overlap. And we could say this has 4 carbon sp3 connected to hydrogen 1s sigma bonds. This wavy line is just, I'm trying to describe what that is. You don't like that wavy line? Don't do that. Then just write this and point an arrow at that, right? It's a carbon in parentheses sp3 connecting to hydrogen in parentheses 1s. And it is a sigma bond because obviously it's one lobe touching one lobe. Do you see that? Right? Okay, that's easy enough. Things are about to get a little bit more difficult. You got a carbon to carbon. And this time I want to draw a carbon to carbon. Yeah, let's start from here. Let's do that with hydrogens all around. I'm going to speed this up a little bit. Then I'm going to draw a carbon to carbon double bond with hydrogens all around. Then I'm going to draw a carbon to carbon triple bond. That's a carbon sp3. And that connects to another carbon sp3, right? Here's how you do this. I'm going to draw that bond first. I'm going to draw a carbon with a sp3 lobe. And then past this, how do I draw a carbon to carbon sp3 to sp3 bond? How do I do that? I drew carbon, I drew a lobe. Should I draw carbon over here? No, that's too close. Carbon needs to be sort of out here so that it can have its lobe overlap that carbon's lobe. That's an sp3 overlapping an sp3. Now what? Put together some of the crap that I had on the board a moment ago where you have the sticks in the plane of the board, wedge and dash. Look at this. Carbon has one stick in the plane of the board this way. It needs another stick in the plane of the board. It could be this way or it could be this way. Do you see you have to have an angle between the two sticks that are on the board? If I decide to put the stick this way, that means the wedge goes out of the board and the dash goes into the board. Do you see how that worked out? On this side, I can decide to put the stick in the plane of the board up, or I could put the stick in the plane of the board down. Do you see that? And if you've gotten into chapter 2, you'll realize that that is actually the difference of Newman dihedral rotational profiles. Anyone got into chapter 2? So the stick in the plane of the board this way, just to make it different than that side, I'm going to put the stick in the plane of the board this way. That means this is the wedge and that's the dash. Do you see that? And then over here, I could put a hydrogen on the outside, circle it, hydrogen on the outside, circle, hydrogen on the outside. I'm not really circling it, I'm drawing the spherical orbital around it. Here's a hydrogen with a spherical orbital, hydrogen, spherical orbital, hydrogen, spherical orbital. And now I have to describe two different bonds. I've got to describe this one right here, and I have to describe this one right here. That one right there has already been described. It's a carbon using an sp3 to a hydrogen 1s sigma bond. But this is a carbon sp3 connecting to a carbon sp3 sigma bond. By the way, does anybody remember why we went on this crazy orbital mission? There was one example that I said we really need to understand in a complicated way, and then we went on this crazy orbital mission, and then I started talking about wave dynamics, quantum mechanics, and so on. I drew resonance contributors, and I said, what's the hybridization of this atom? And in one picture it might have been sp2, and the other picture might have been sp, and I said, it's not sp2, it's sp. To understand how that goes, we have to understand orbitals. To understand then understand hybrid orbitals. We went on this whole mission. Hopefully by the end of today, we could go back to that resonance problem and fully understand exactly why we needed to cross out one of them and not the other. I think we're close. Do you see this? Are you good? Okay. This is going to pose a new little bit of a problem, so we have to deal with it this way. When you have a carbon that's sp3, an sp3 carbon, I'm not drawing that yet. Just saying carbon that's sp3, it's got 4 orbitals, 1, 2, 3, 4, tetrahedral. When you have a carbon that's sp2, everybody knows it's trigonal planar, right? You know that it's trigonal planar. But there's still that p orbital that's left over, right? If it's sp2, it's got, look, every carbon has s, p, p, and p. And if it's sp2, it's that, but there's a p orbital left over. And the question is, it's not just the orbitals that are sp2. They are trigonal planar relative to each other, but where the hell is the extra p orbital? Where does that go? So an sp2 carbon, there's two ways I could draw it. I'm going to draw it first in the plane of the board, right? So it's trigonal planar, but flat along the board. That means it's got one orbital this way, one orbital this way, one orbital this way. That's one way I could draw it. I could draw it differently. I could take it and I could turn it. I could turn it like this and have it in the plane of the floor. Do you see? Here's another way I could draw it. I could draw one orbital this way, one orbital in front, and one orbital in the back. This is this. I just took it and I turned it. Let's make sure everybody's on the same page here. Here's 3 markers that are trigonal planar. Here's 3 markers that are trigonal planar, right? Flat with the board. I could take them and I could turn them like this, and now they're flat with the floor, right? Okay. What is hybridization? It means mixing. It means orbitals have mixed. When the orbitals for sp3 have mixed, that's why you have the orbitals going in every single direction. Hear this out. If I have a Cartesian coordinate axis with an x, y, and z, right? Where is the s orbital? The s orbital is just kind of in the middle. But you also have a px, a py, and a pz, right? And do you notice that the px goes in the x-axis, the y goes in the y-axis, the z goes in the z-axis? So when you're using sp3, you are using all 3 axes. You're using the px, py, and pz. That's why it's in 3-dimensional space. But if you're doing an sp2, you are only using 2 of these axes. For example, let's say I'm using the py and the px. None of it is going in the z. None of it is going in the z. This is why the result is trigonal planar in the x and in the y. None of it goes in the z. But there is a leftover orbital. Which one? The pz. And where is that? It's going to be by itself in the z. Do you see this? Do you see? Think about this just mathematically. I don't need you to picture how this mixes together and looks like this. Just, don't see with your eyes, see with your mind is what I'm trying to say. if there are orbitals in the directions, lots of slippery notebooks today. If there's orbitals in the directions of x, of y, and of z, and I use all of them, my result will be in directions of x, y, and z. But if I'm only using two of those orbitals, px and py, right, then my result will only be in the pxn and the py. The hybrid orbitals will only be in the px and the py. They'll be flat. But then there'll be that leftover pz orbital going in front and in back. Do you see that? For example here, let's say I made a hybrid out of S and PX and PZ, right? Do you see I made a hybrid out of S, PX, and PZ? That means my orbitals will go in the positive PX and then in the negative PX and in the positive PZ. Do you see this is just along PX positive. This way is negative PX and into the board is positive PZ. And this way is negative px, and out of the board is negative pz. None of this is up in the py, right? Now imagine I have s, px, pz, and py. And I made a hybrid out of this, sp2, right? Do you see I have a leftover py that didn't hybridize, so none of these orbitals are in the py, but I will have a leftover orbital called py, and that py would look like this. By itself, didn't mix. We say that these orbitals are orthogonal. Or it's in the book, orthogonal. It's a physics term, orthogonal. These orbitals are orthogonal to this orbital. Orthogonal sometimes is easy to just see as 90 degrees away, but really orthogonal means as far away as possible. Because if they're as far away as possible, they're not going to mix at all. So I tried my best to make you understand what this looks like, but we can kind of recall something in Gen Chem to see what this actually looks like. This has a shape of tetrahedral. And I know when I erase the p orbital over here, sp2, you've been trained to think that's trigonal planar. And it is. It's trigonal planar, right? Whether I draw it like this, it's trigonal planar, or draw it like this, it's trigonal planar. But when I include the last orbital, the p orbital, do you see it has that shape called trigonal bipyramidal? Do you remember that trigonal bipyramidal? The 5 orbitals, there was a trigonal planar plane, and then a linear one in between. So the sp3 orbitals are in the trigonal planar plane, and the unhybridized p orbital is in the linear portion. This is sp2, 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 and this is the unhybridized p, the one that didn't make it into the hybrid. Does that make sense? You have to be able to understand this. You have to be able to picture this. If I draw the p orbital in some direction and then say where are the sp2 orbitals, your brain should make you realize they're perpendicular to that. Do you see how my palm is in the plane that the p orbitals would be? The sp2 orbitals would be? If the sp2 orbitals are like this way, and this way, and this way, planar over here, the unhybridized p orbital should go up and down. If the sp2 orbitals are like this, planar like this, the p orbital should go in and out. So if I show you sp2 orbitals, you know where p orbital is. And if I show you where p orbitals, you now should know where sp2 orbitals are. They're all perpendicular to each other. Do you picture this? So let's draw this. See, we're trying to make sense out of stuff you already know, but like completely make sense. In Gen Chem, it's enough to say this is trigonal planar. Why is that enough to say? This atom is trigonal planar because it's sp2 hybridized. This atom right here is trigonal planar because it's sp2 hybridized. But just because I have a trigonal planar atom here and a trigonal planar atom here, who's to say the whole molecule is planar? Do you understand the question? So look at the solution to this. Look how we put the parts together. Is that planar or not? I'm going to start drawing this carbon. I could start drawing this carbon. You know the hybridization of this is sp2, right? And you know the hybridization of this carbon is sp2 also. I'm going to just start drawing one of the carbons. I'm going to draw the sp2 orbitals. How can I draw the orbitals? As long as they're in a plane, it doesn't matter if I draw them in a plane this way or in a plane this way. I'm going to draw them in a plane like this, right? So this carbon, first of all, is connected to this carbon right here. obviously, because it's got at least a sigma bond. It also has a pi bond, right? Now this carbon is trigonal planar. Do you see which way I could draw? Don't copy this, but just look at what I'm doing. I could draw this right here. And do you see I've demonstrated it's planar in the plane of the board? Or I can draw it like this. And now I've demonstrated it's planar in the plane of the floor, right? Like this is going this way and those two orbitals separate, like that, right? Just because these two orbitals go front and back, who's to say that on this carbon, its sp2 orbitals also go front and back? This is a big question here. Here's why, because they go front and back, these also have to. Look what's going on. This carbon is trigonal planar, sp2, 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 and it's connected to a hydrogen here, it's connected to a hydrogen here. Now what else is on this carbon? It's sp2 hybridized, but every carbon has spp, and if it's sp2 hybridized, it's got a leftover p orbital. And if it's sp2 hybridized in a plane of the floor like this, then the p orbital that we just keep talking about is this way, right? So I'm going to draw that p orbital, and since it's a p orbital, I have to shade it on one side. It doesn't matter if you shade it on the bottom or the top, that's irrelevant. Here's my shading. I'm not the best artist. I did an okay job. Now, let's think of several cases. Everyone paying attention? Let's think of several cases. This has to be trigonal planar. What if this was in the plane that's not the same plane as there? Meaning the hydrogens are out and out. What if this was not out and out? What if this was up and down? Do you see that? What if that was up and down? Is that okay? If this sp2 orbital is up and this sp2 orbital is down, where is the unhybridized p orbital? This would be in and out of the board, right? What do you see between these two carbons? A sigma bond and a pi bond. How do you get a sigma bond? These orbitals overlap like this, so we see a sigma bond. But with the way that I draw it, demonstrate a pi bond. Meaning if this sp2 orbital is up and this sp2 orbital is down, that means the p orbital will be out of the board and the p orbital will be into the board. And let's say I shade it. Is this a pi bond? When one p orbital is like this and the other p orbital is like that, is that a pi bond? What's a pi bond? They all have to be parallel, right? So actually, we drew something wrong here. Here's my point. Here's how we should have drawn it. We don't automatically know where the sp2 orbitals are. But what we know is, if this p orbital's up and down, and there's a pi bond, then this p orbital has to also be up and down, and shaded the same way that one's shaded to become a pi bond. Is anybody with me here? Now, once we know that this p orbital's up and down, we then could figure out where the plane of the molecule is. Remember I said if you know where the plane is, you could figure out the p orbital. If you know where the p orbital, you can figure out the plane. If this p orbital is up and down, then the plane of the trigonal planar cannot be up and down. It has to be in every other direction. So it could be right, left, in, out, but it can't be up and down. That means the orbitals are going to be in front and in back, and that means the entire molecule is trigonal planar. Do you see that side is the same plane as this side? Are you with that? So important. How do we describe this? I can do this. I can put an arrow from here to here. See how I'm sort of touching these orbitals with that, sort of like an arrowhead. I could put that and write, this is a carbon 2p connected to carbon 2p pi bond. You see that's a 2p orbital from a carbon and a 2p orbital from a carbon, and that's the pi bond. Now I could draw over here and write this is a carbon sp2 connected to carbon sp2 sigma bond. So this has a carbon sp2 sigma bond, and also a carbon 2p pi bond. The main question is, does your picture look like mine, or does your picture look like crap? Because my picture doesn't look that great. So if yours is any worse than this, then it's really bad. Okay. What is this? What kind of bond? Can you describe it? This is a carbon but it's not sp3. It's a carbon that's sp2 connecting to a hydrogen that's 1s, because hydrogen's always 1s, and it's a sigma bond. Do you see we've described several features of this? Now I'm going to do the last one. I'm going to bring it back to here. Hydrogen, carbon, triple bond, carbon, hydrogen. This carbon is sp. Now let's say it used the spx, s and a px. That means its hybrid orbitals, sp, are not in the y and not in the z. Does that make sense? Let's say you use the z, then it's not in the x or the y, right? You see it's only one-dimensional. Therefore, sp is linear. That makes sense? This is sp. That means the carbon still has another p orbital and then another p orbital after that. Right? Because can we all make sure to process that? That any carbon has sp-p-p. We said that originally. Then anything on the second row has n equals 2. That means it has s and p has 3 of them. So it's sp-p-p. And if you see a carbon that's sp, that means it's p and p left over. Right? Now there should be here p and p left over because there's sigma bond that's made out of sp, but then there's a pi bond, so you need a p orbital for that pi bond, and then there's a second pi bond, you need another p orbital for that second pi bond. Every pi bond you see needs its own unique p orbital. You can't make a p orbital make more than one pi bond. The p orbital must be participating in its own pi bond. So how do you draw that? You draw a carbon, and this is easy to draw because the whole thing's linear. This is linear and this is linear, and when it's linear, it's just going to keep being linear. So this carbon has an sp orbital this way and sp orbital this way. It's connected to a carbon that has an sp orbital this way and an sp orbital this way. All the way left is a hydrogen atom. All the way right is a hydrogen atom. And because this carbon, let's say we have these coordinates, x, y, and z. Clearly, the whole molecule is along the x, right? So it must have used px. But then there's py and pz left over, right? So I'm going to have to draw a p orbital in the y. So then this carbon has a p orbital in the y. I could shade the top, the bottom. Really doesn't matter too much. Let's say I shade the bottom. But if that's true, then that has to have a pi bond to the other carbon. So I'm going to draw another p orbital on that other carbon and shade the same exact side to make sure that it has a pi bond. Here's some interesting questions that we can get from chapter 2. If this was a physical molecule, do you remember you had those molecular model kits, like when you had the aspirin lab, not the aspirin lab, wrong. When you had the maleic acid, fumaric acid lab, where you had the balls and sticks and you connected them. Professor, is this right? It was funny as a professor. So you have to connect the balls and sticks in a cis way. Great. And then you have to have it sign off, and then you leave and you have to reconnect it in the trans way. Some people just got it, right? They just unclipped it, turned it around, and clipped it back in. And then you see some students go to their desk and take the whole damn thing apart. And you're like, you guys like doing extra work, right? Imagine I had this in a ball and stick model, right? If I held this side and I asked you to go to that side, would there be any kind of significant or just whatever barrier of rotation? Would there be any reason why you can't rotate this side? The answer is no. You should be able to rotate this side fairly easily. Grab this hydrogen and spin it. This whole side spins and this side stays the same. That's called a dihedral rotation. That's what we're going to be talking about in terms of Newman's. Can you see how this is different? If I asked you to hold this side still, I wouldn't be able to rotate this, because if I rotate this side, the p orbital rotate, and rotating a p orbital away from a p orbital means I'm breaking the pi bond. So I would have to put in however much energy to break the pi bond. Do you see what we're discussing here? This is py, let's say, and py overlapping, but this is missing something. What is it missing? There's another p orbital to make another pi bond. Let's say the pz. So I could draw this out of the board and into the board, out of the board and into the board. This is really difficult to kind of draw on a picture, on a piece of paper. This is not like down in the left corner. This is going in and out of the board. It's a p orbital, so I have to shade one side of it, right? Doesn't matter which side I shade, absolutely not. I like to shade the front because it tends to clean up the picture a little bit. It makes it look a little more 3D. But there is the sigma bond and 2 pi bonds. I'm not going to write this down. You could write this down for homework. This is a carbon sp connected to hydrogen 1s sigma bond. This is a carbon sp connected to carbon sp sigma bond. And this right here is a carbon 2p to carbon 2p pi bond. And this other one's a carbon 2p to carbon 2p pi bond. You see each p orbital needs to partake in its own pi bond. I hope you understood this. Because from here comes this question. What is the shape of molecules that are called allenes? Allene is a molecule that has a cumulated pi bond system. Cumulated pi bonds. So what are these cumulated pi bonds? The smallest allene looks like this. It's 2 hydrogens on a carbon, double bonded to a carbon, double bonded to a carbon with 2 hydrogens. Cumulated is double bonds that just go one after the other, no breaks in between. Like, look, if I draw this, this has a pi bond that has another pi bond, but has nothing to do with cumulated. If I do this, this also has nothing to do with cumulated. In fact, this does have a name. The system is called conjugated, and this has resonance. But cumulated means nonstop. So if I have a double bond here, I also have a double bond here, I also have a double bond here. Do you see that? Now, it doesn't have to be in the whole molecule. Let's say this is a molecule, then this section of it is cumulated. You see what I'm showing you? So the simplest, of course, is this. And then you could have H2 carbon, double bond, carbon, double bond, carbon, double bond, carbon, H2. And it could get bigger and bigger and bigger. You start with 2 double bonds and 3 double bonds and 4 double bonds and 5 double bonds. It could go to 100 double bonds. Large cumulated system. Ignoring the lesson, if I asked you what the shape of this molecule is, you would say the whole thing is trigonal planar. Why? Because this carbon is trigonal planar, this carbon is linear, and this carbon is trigonal planar. So you got trigonal planar, the whole thing's trigonal planar. It's not trigonal planar. So I'm going to do this one with you, but for homework, I want you to do the next one and the one after that. So for homework, I want you to draw CH2, double bond C, double bond C, double bond CH2, and then at least do this one. But I would definitely want you to do this one also. Double bond C, double bond C, double bond C, and then a double bond CH2, right? So there's 2 cumulated, 3 cumulated, 4. We're going to do 2, then for homework 3 and 4. Okay? Okay. How do you draw it? Start on the left side. This is a carbon that's sp2. This is a carbon that's sp. This is a carbon that's sp2. Everyone sees that? If it's sp2, there is an unhybridized p orbital left out. That's not part of the hybridization system, right? So I'm going to draw that up here just to remind myself there's an unhybridized p orbital. Over here, there's an sp2. That means there's 2 unhybridized p orbitals. So I'm going to draw p, and above that, I'm going to draw another p. And if this is sp, there's 1 unhybridized orbital. Do you see how all of that makes sense? Because look, the middle carbon has a pi bond to the left, so it's got to use the p orbital that it has to pi bond to a p orbital on the left. But then it's got a pi bond on the right. It has to use a different p orbital to pi bond to the thing on the right. So look, the point is, if you ever see a molecule that has any amount of pi bond, it has to have p orbitals. You can't have some amount of pi bond with no p orbitals. Does that make sense? That's the answer to the resonance question. That's the answer to the resonance question. Let's answer the resonance question before we do this. Check this out. If I have this, if I have that, this is called the formate ion. We have seen this before. If this resonates, then the electrons from down here go this way. The electrons from over here go this way. And here is your resonance contributor. You know, we haven't done resonance for like a lesson and a half. That doesn't mean you ignore everything that we taught you. Pretty soon, the professor or lab instructor should hand out a resonance worksheet. Ignore the answers, because on that resonance worksheet, the answer key is absolutely wrong. How do I know? Because if you type in resonance worksheet to a Google search, it's the first thing that pops up. And whoever also pasted the answer key there, it's the wrong answer key. Right? I think professors sometimes give the answer key for organic chemistry classes wrong on purpose, because you can't learn this class from an answer key. So anybody who memorizes the answer key the day before the exam is memorizing wrong answers to put on the exam. It's almost like a joke that the professors are pulling. Like, here, memorize this wrong stuff. Haha. It's only right. If you're going to wait till the last minute, you might as well fail. Then maybe next time you won't wait till the last minute anymore. And then you'll do it the right way and get a whole lot out of it. Why did I lose points on the exam right now? Thank you. Somebody's listening. That was fast too. Fast answer. Look, question. What does this look like in this picture? What does a hybridization of that look like in this picture? It's an oxygen with 1, 2, 3, 4 domains. It looks sp3, right? I'm not even going to handle the whole molecule. I just want to point out like at least one part of it, right? That oxygen. Where is that oxygen in this picture? In this picture, this is the oxygen. And it looks 1, 2, 3 domains. It looks sp2, right? What did I say to do before we went on this huge mission of orbital crap? I said, if it looks sp3 in one picture and it looks sp2 in the other picture, go with the lowest value of p. Cross this out. Now we get to see why. This should be like, oh my God, that makes so much sense. Check this out. Let's draw the hybrid. Let's draw what it actually kind of looks like all at the same time. Didn't we say we have to mix these together and do this? Carbon, oxygen, oxygen. It's not a single bond in between here and here. It's not a double bond in between there and there. It's a mix. It's a perfect 50-50 mix. It's a hybrid. It's 1.5 bonds. I'm going to draw 1.5 bonds, sort of like that. And it's not a double bond up here. It's not a single bond over there. It's 1.5 bonds, right? 1.5 bonds, right? Bond order 1.5. It's not a negative charge here. It's negative and 0. That means it's negative 1/2. It's not 0 up here. It's 0 and negative. That means it's negative 1/2. We know about the charge distribution. Now, check this out. This should be like, oh my God, that's so obvious. If you learned everything that I wanted you to learn, not even into an amazing high order, just have the general ideas of what we've covered today. Look, how could this be sp3 for this oxygen? How could it be sp3 when all at once it's got some amount of pi bond? And if it has some amount of pi bond, doesn't it have to have a p orbital to have some amount of pi bond? And an sp3 has no p orbitals to have some amount of pi bond. sp2 has a leftover p orbital to have some amount of pi bond. Resonance moves through p orbitals, and any atom participating in resonance must have p orbitals. So do you see it can't be sp3? It should just be overwhelmingly obvious that if it's sp3, it can't do resonance. So even if it looks sp3, it is not sp3, because it has to have some amount of pi bond electrons flowing through there. Imagine everything I talked about for 2 hours today was all just to say that. Then it was still worth it, because you actually understand this at this point. And if I just said that, you wouldn't understand it. Most of the times then when a student tells me, I can't do this question in Orgo, how do you do this question? People come to a tutor, they're like, I can't do this question. And then the tutor shows it to them, they think they know it, and then they get it wrong. Why? It's not the question that they're missing. They're missing all the background information to make that question make sense. And not just make sense, but for you to realize, yeah, it makes sense and everything like it makes sense. So when you see any variation of it, you'll still get it right. This is what we're looking to do. I hope everybody sees this. Now imagine in the hybrid, the bond order was not 1.5, but in the hybrid, the bond order was 2.5. That means it had something between 2 and 3 pi bonds. Between 2 and 3 bonds. That means it had 1 sigma and like sort of 1.5, which means 2 pi bonds. To have 2 pi bonds, it can't be sp3 or sp2. To have 2 pi bonds, it has to be sp, because to have 2 pi bonds, it has to have 2 p orbitals. Does that make sense? Anything more than 1 bond means it has a p orbital. Anything more than 2 bonds means it has 2 p orbitals. Otherwise, it can't do that, right? Because you can't just put electrons without an orbital. That's breaking all of the rules. That's why the octet rule exists. If you look at the end of chapter 1, they show you this strange thing, and it looks maybe like a mistake. This compound called an amide. Did anybody see this at the end of chapter 1? It asked what the hybridization of this nitrogen was, and people think it's an error, and sometimes even recitation instructors say, yeah, it's an error. If you saw a nitrogen like this, what is the hybridization? It answers it's got 1, 2, 3, 4 domains. This nitrogen is sp3. What's the hybridization of this nitrogen? The book says it's sp2. Doesn't this nitrogen look exactly like this nitrogen? There is a difference. And the difference is nothing you would predict. The difference is something we're going to discuss for like 20 minutes here. This comes from a very important connection called the amide bond. This bond right here between a double bond O and an N is called an amide bond. Very commonly mispronounced as amide. Have you ever said amide? It's not amide, it's amide. You could say amide for the rest of your life, but I'm a biochemist, and this is the bond that's important in biochemistry. Biochemists are the one who studied that and named it. In biochemistry, if it's an amide bond between two amino acids, it's called a peptide bond. We call it amide. It's not amide. So anyone who says amide is just mispronouncing it. Sort of like when people say Nevada. You know, the state Nevada. It's the wrong way to say it. How do you know it's the wrong way to say it? Just go to that state and ask somebody, what do you call this place? And they'll be like, Nevada. So it's not Nevada, it's Nevada. Does pronunciation matter? No, but if you find yourself working in a biochem lab doing biochem research and you call it an amide, everyone's going to be like, all right, this person doesn't know anything. It turns out that this is the bond that connects amino acid to amino acid, and it's got unusual strength. It's nothing you should predict, because what we've learned from resonance would say this shouldn't have resonance. Because if you move, look, do you see this is the ABC scenario? This is atom A with a lone pair, then there's BC double bond, and if you move the electrons this way, you create charges rather than distribute charges. So you would never predict this has resonance. But for a reason, this kind of breaks rules a little bit, and this really does have resonance. And not a lot. The idea is it doesn't have to be a major contributor. It's just that when you're doing this game of asking about hybridization, you count all contributors that are not negligible. So if it's a negligible contributor, you ignore it. Do you hear what I'm saying? If it's a negligible contributor, you ignore it. But if this has any real contribution going this way, and if this right here is any contributor more than negligible, if this counts at all, that means oxygen looks sp2 up here, but it looks sp3 over here, and we've already said choose the lower value because in resonance, right, there's some amount of pi bond, so it can't be sp3, but more importantly, the nitrogen, while it looks sp3, is not, because if there's any amount of pi bond, then the nitrogen is actually sp2, and we're going to develop a rule for this. We're going to say that whenever a nitrogen is covalently connected to an sp2 atom, it also is sp2. Do you see this nitrogen is connected to an sp2 atom? That means it will resonate with that sp2 atom and also be sp2. I took a far detour. I was going to draw this, and then I said something, and then I said something else, and then I said something else after that. I didn't forget, I'm still going to draw this, provided we have enough time. And we do. We got 20 minutes. So since I've said this, let me just finish this idea and then finally draw that and then leave you with homework. Biochem really cares about two bonds. Two bonds. Biochem cares about this bond, not the whole group, but really the bond between what we call a carbonyl. A carbon double bond O is called a carbonyl. A carbonyl could be a ketone and aldehyde, a carboxylic acid, an amide, an ester. It could be all kinds of things. It just depends on what the carbon double bond O is connected to. In this case, the carbon double bond, though, is connected to a nitrogen. You call it an imide. Biochem really cares about that bond because this is the bond that's like amino acids and proteins. That's the bond that amino acids use to make proteins, peptide bonds. The other bond that biochem cares about is a nitrogen. I don't know what's here, but a nitrogen connected sort of like to a benzene ring. Why I say sort of like to a benzene ring? Because benzene rings are aromatic systems, and you don't have to be connected to a benzene ring, but specifically to an aromatic system. Let me give you an example. Here, this substance this is the C in ATCG. Do you know what a pyrimidine is? Purine, DNA, ATCG. This is the nitrogenous base called C, right? What's important? Have you ever seen a DNA double helix? A DNA double helix has two strands, and each of them have hydrogen bonds across, and if you look at how the nitrogenous bases are hydrogen bound to each other, they're very flat planar, right? And if they're very flat planar, that tells you that they're sp2 hybridized. What's the point? This whole thing is flat planar, and this nitrogen is hydrogen bonding to the other side. And that means, what is its hybridization if I draw out these H's? It can't be tetrahedral or anything like that, because it has to be hydrogen bound in DNA in that flat planar way. This nitrogen is sp2 hybridized. Why? Because it's a nitrogen connected to an sp2 atom. Automatically, that means it resonates. Do you see what I'm saying? What's the hybridization of this bottom nitrogen? It's sp2 also. Do you know why? Because it's connected to an sp2 atom here, or it's connected to an sp2 atom here. That means it can resonate those lone pairs. Point is, you're going to have to just remember that exception. And a nitrogen that looks sp3 connected to an sp2 atom is automatically sp2. And we're not fully done with chapter 1 because we're going to have to talk about that a little bit more. I'm going to give you some examples, and then we're going to jump right into chapter 2. So your job for the next lesson is to read at least through sections 2.4. At least read 2.1, 2.2, 2.3, and 2.4. And when I say read, I mean like carefully. Don't do it like Tuesday morning because you didn't have time. And don't even do a Monday night. Well, actually, our next lesson is Thursday. Don't do it tomorrow night, Wednesday night, or Thursday morning. It doesn't work. You're going to have to try to read it today, and then tomorrow, and then the next day. Slowly. Let it permeate in your brain. You know, knowledge in this field, knowledge in terms of science, MCAT, DAT, PCAT, OAT, it should be like cooking something, but specifically cooking like a stew to get flavor, right? How do you cook a stew to get flavor? Do you cook it at high heat for 5 minutes? You cook it at low heat for 10 hours. It's low and slow. You let it absorb deep. Not superficial bullshit. You know what I'm saying? Because then it's just a waste of time. Studying the night before, you're just wasting your time. Might as well get drunk and hope for the best. How are we going to draw that? I'm going to try to prove that that's not trigonal planar, and we have to be careful on how we draw the orbitals. I'm going to start with this. Here's a carbon. What is that? That's an alene. Accumulated pi bonds. I'm going to start with this carbon. This carbon has sp2 orbitals. I could draw that in the plane of the floor. I could draw that in the plane of the board. I could do all that, right? For no reason at all, I'm going to decide to draw it in the plane of the floor. So here's an orbital to the right. Here's one coming out of the board. Here's one going into the board. Now, why didn't I do this? Why didn't I draw it like this? An orbital to the left and one out of the board and one in the board. I know that I'm going to need to connect it to this next carbon, so I want the one on the right to be straight so that I could connect it to the next carbon. Do you see what I'm saying? Like, I could draw this. It's just going to make my next carbon come out of the board or go into it. So it's going to be all strange. So I did that. There's two hydrogens over here. I'm going to draw a hydrogen and put an s orbital around it, draw a hydrogen, put an s orbital around it, and what's that way? Past this way is a carbon with an sp orbital. Now check this out. Do I know where the other side of the sp orbital is? The answer is yes. Because it's linear, I know it's just going to keep going straight, so I'm going to draw this carbon's sp orbital like this. But use logic. After this, I know that the middle carbon is going to be connected to that last carbon with a sigma bond, so I know that's going to be straight. But do I know where the other orbitals are over here? The point is, it's not linear anymore. It goes out. And it could go out this way or out this way. It could go out in any angles, right? If the next atom was sp, I could just keep drawing it straight. Do you see what I'm saying? Like this has more than one dimension to it. This has 2 dimensions. It goes this way and out and in, right? And if I drew this trigonal planar in the plane of the floor, and then I have to go linear, I could keep going linear until I get to the next trigonal planar. The next trigonal planar, I don't know if that stays in the plane of the floor, goes up in the plane of the board. I don't know which way it goes. You know what's going to tell me which way it goes is the orbitals, the p orbitals. This has a p orbital. We all should know that's going up and down, right? If this is going trigonal planar in the plane of the floor, the p orbital is going up and down, and I could shade one side of it. Shade whatever side you want. It doesn't matter. Top, bottom. Now you know that that sp2 has a p orbital connected to a p orbital and a pi bond for the middle. So this is going to link to a p orbital in the middle. In the middle I draw another p orbital. I shade it. Do you see I shaded the bottom? And now I know that's a pi bond. What else? This has another p orbital. You see it's got sp orbitals on the left and right. It's got a p orbital up and down. That means it's got another p orbital in and out. Did you notice that when it's sp2, it's trigonal planar, and then the p orbital is bisecting it, so it's like trigonal bipyramidal? But when it's sp, it's linear, and then there's a p orbital and another p orbital. It's almost like it's octahedral. It's 2, 4, 6. You see that? So if I draw the next p orbital, I could draw it like this or like this. Just to vary it, I'm going to draw it in this direction, right? That's out and into the board, right? Now that means that there is a p orbital on this that is overlapping this p orbital right here, and it's going to be shaded in the same direction. Does it matter which way I shade this? Not really. So I'm going to shade it in the front. Is it always not going to matter? No, and sometimes it matters, sometimes it doesn't. But there's no orbitals before it to bother the way I'm going to shade this, so I'm shading this in the front, right? That means I'm going to shade this in the front also. So do you see the first pi bond is with p orbitals up and down, and the next pi bond is with p orbitals in and out? Final question. Most important question. Where are the other sp2 orbitals? See, these sp2 orbitals are in and out. Does that mean those sp2 orbitals have to be in and out? They don't. They're governed by where the p orbitals are actually. And do you see, since the p orbital's in and out, the sp2 orbitals can't be in and out? They have to be the other way, which is up and down. So over here, the sp2 orbital is up and down, and the hydrogen is over here and over here. What's the point? It's wrong to draw this like this. And on an exam, it'll probably be drawn like this. It's wrong to draw it like this, because this is not flat planar in the same place on both sides. Do you see that indicates that it more looks like this? That here it's a hydrogen out of the board and into the board, while here it's a hydrogen up and down. Do you see how that works out? We don't see that's in and out of the board, while over here it's up and down. So what I need you to do for homework is this one, and then this one, and see if you could recognize any kind of pattern, and that means we're essentially done with the chapter. Just 1 or 2 more like advanced questions to do with the chapter, and then we can move on to chapter 2. And I think that's the proper amount of time. So thank you for your participation, and hit like and subscribe.